understand, Lee, is that you begin speaking about yourself, your trajectory. Yes, 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 your career, your experience in Mascoma, your experience in startups, idea, academic experience, connection, formation of people. That really we want to understand how to be a Lee Lynd. Yeah.
Well, let's see. Tell me
Sorry,
a little
just a second. Just a second. We have not yet started. If you
Yes.
agree, we can start. And if you have a presentation, you can share from
Yeah.
your point, right?
Yeah, I do agree. We can begin. Could you tell me a little bit about the audience, Gonzalo? Who am I talking to?
Okay. We have two kind of audience, the people that are students, PhD student in our program, and also some external people that come from different areas, but everything connected to bioenergy.
Okay.
And this is transmitted through the YouTube, and
Yeah.
will be saved in our let's say bioenergy library of the
Very
YouTube.
good. Okay, well, let's get started so I can share my
Yes.
screen at any point.
Just second, just second. I
Very
will
good.
admit the people.
Yep.
The people is coming. They will be entering during your presentation. And Tainara, we can begin the transmission to YouTube, okay? We are online. Okay, great. So
All set?
yes, then let's then start. Good afternoon to everybody. Lee Lynd, thank you very much.
Yep. Just plugging in my computer to avoid a little energy shortage here.
Yes, take your time.
Yeah, no problem. Okay.
This is the good thing that we got from the pandemics.
Yeah,
that
exactly.
We can have you can have you here from your house or your office is great.
Indeed.
Lee, thank you very much for accepting you are part of Unicamp today, and this is great. And as we have spoken before, I would ask you to start explaining your career, explaining your ideas in funding, yeah, Mascoma and the other initiatives in 2G. It's a big pleasure to have you here, a really big pleasure. And as I said to you, this is going to be recorded, and this presentation will be stored in our bioenergy videos so that people can look at it in the future. Thank you very much, Lee.
Great, Gonzalo. Good to be with you, and good to be with you, members of the class. You know, I certainly can talk about myself and my career. I had prepared a slide presentation. I know we only have an hour, and with your indulgence, I'm going to race through the slide presentation just to give you a sense of what I think about and what I'm up to. It's too much stuff. I apologize in advance. And then hopefully I will be successful at leaving time for discussion. And we can either focus at that point on the personal aspects or the technical aspects. But so I'm going to get started with your indulgence. And I would be a pleasure to meet with any of you next time I'm in Brazil, which I think will be the end of July or early August. So I'm going to talk to you about what I call 2G 2.0. 2G, of course, refers to second generation biofuels. We've been through 2G 1.0 in the last 15 years or so. Although there have been some successes, frankly, progress was nowhere near what people expected or hoped. By the way, those of you working on agave, I particularly like that picture in the middle on the left. So keeping this simple, I'm going to talk to you about the context for bioenergy. I'm going to talk to you about consolidated bioprocessing with co-treatment and a few organizations I'm involved with that are trying to make this happen in the world. And so on we go. The world is changing fast, whether you look at atmospheric CO2, population, oil consumption, what have you. This has been enabled by a succession of technological revolutions, the Neolithic, the industrial, the information. And we now need to be launching a an additional industrial revolution, the sustainability revolution, keeping above all else two things in mind: a shift in reliance on sustainable resources and processes, and that although we live in a rich world, most of the inhabitants are still poor. We have to never forget that and try to simultaneously solve these problems. So if you look at biofuel feedstocks, there's a lot of them. I'm going to be talking only about second generation lignocellulosic feedstocks here. We could discuss other ones if you like. And so first of all, to point out that this material is cost effective, it's less expensive on a dollar per gigajoule basis than petroleum. So if you look at biomass in a dry ton all the way up to $100, and you can get a lot of biomass for less than that, that corresponds to oil at less than $38 a barrel. And so high processing costs are the key barriers to overcome. The last decade, as I mentioned, biofuels fell far short of expectations while other renewables exceeded them. So global investment down here, the lower right, global investment in biofuels, wind and PV was about equal in the 2006 timeframe, and now is vastly greater for PV and wind. PV and wind overshot expectations. Biofuels, especially second generation biofuels, grossly undershot expectations. So here in the United States, we had a renewable fuel standard, somewhat similar to your Hanova Bio. And if you notice this, in 2017, actual ethanol production was short of the target. This is a log scale, folks, by 3 orders of magnitude. So really didn't fulfill the potential in that time frame, and global investment went down dramatically. However, I want to acknowledge with great respect that Raízen and Brazil, well, Brazil is the global leader in second generation biofuels today, with an unparalleled commitment by Raízen to build 20 second generation plants. So I honor that leadership. It's globally unprecedented. My prediction, though, is that the current processing paradigm based on fungal cellulases, thermochemical pretreatment, which we'll talk about in more detail, I think it will enable, and it's already enabling, the launch of a cellulosic biofuel industry based on co-located plants processing sugarcane in Brazil. But I think it's going to remain too costly for standalone second generation ethanol production and for most other feedstocks. And whether that prediction is right or not, look, if we can get technology that will let us do things less expensively, that's a good thing, whether or not the current technology can fully launch an industry in multiple locations, multiple feedstocks for standalone plants. So I want to talk to you about biofuels and negative emissions. If we look at the carbon cycle, the idea of bioenergy is to take some photosynthesis and therefore displace greenhouse gas emissions, but also, and this is increasingly important, to capture carbon dioxide. And so I want you to keep that in mind. Displaced emissions, fossil fuels we don't burn because we burn biofuels, and captured emissions, which are basically taking CO2 from the processing environment and putting it, or system, and putting it in the ground. So there's broad consensus that we will need negative emissions to stabilize climate, as illustrated here. And McKinsey, for example, says substantial negative emissions, carbon removals, are needed with emission reductions to avert catastrophic climate change. Interestingly, my friend Pete Smith from the University of Aberdeen looks at different negative emission technologies: bioenergy with carbon capture and storage, direct air capture, and afforestation are the 3 big ones. And as my friend Jim Beilenberg from ExxonMobil says, BECCS is the only option we see that's both carbon negative and revenue positive. And you notice here that direct air capture actually requires about 160 exajoules of energy. That's more than 25% of the current global energy consumption. BECCS in this particular scenario or projection actually produces about that much energy. So in my opinion, we may need direct air capture to stabilize climate. We may need everything to do it, but I hope we can come up with some options that have, in addition to direct air capture, that have more favorable economics and other features. So if you work backward from a stable climate future to the present, most see a large role for biomass, and this surprises some people, but this is from it's actually from the IPCC special report in 2018, and it shows that biomass, primary energy from biomass, is larger than wind and solar combined globally. This is according to the median of 85 1.5 degree scenarios, not only today, but in 2050 as well. And so this is also roughly true that biomass provides about 25% of primary energy in the IPCC AR6 scenario, the IEA net zero scenario, the Shell Sky 2050 scenario. And the primary reason for this is negative emissions, in my opinion. So if we look at the need for biofuels as part of a low carbon energy future, noting that the transportation sector has got the highest emissions in the US, it's the fastest growing worldwide, and it's amongst the hardest to make carbon neutral. We published a paper a while ago with Lou Fulton, who was the two-time lead transportation analyst for the International Energy Agency. I apologize that the slide is not showing with complete fidelity, but I don't want to get into the details anyway. What is listed here are various different sectors of energy utilization, and all the way out to 2075, the contribution of different energy sources. Again, my apology that for some reason that's not showing up well. But my goodness, this has the same problem. I hope I don't see that throughout the presentation. But what's shown in the lower left is if you add all of those together, about 50% of future transportation energy consumption out to 2075, according to the 2-degree scenario, is required from biofuels. And we wrote in that paper, even with aggressive reductions in travel growth, shifts to mass transport modes, strong efficiency improvements, and deep market penetration by vehicles running on electricity and hydrogen, there remains a large demand for dense liquid fuels in 2050, 80% of transport demand, and even in 2075, largely due to aviation, ocean shipping, and long-haul trucking. And Lou, actually more recently than 2021 even, confirms that in his view, that is still the case. So if now you can see some of those categories. I don't know why it's showing up better here, but if you take that plot I just showed you, in round numbers in 2075, about 50 exajoules of transport energy is provided by electricity or hydrogen produced from renewable sources, and that can approach being zero emission. And about 50 exajoules is produced by biofuels. If you look at the displaced, or if you will, mitigated emissions from 50 exajoule biofuels, you just multiply the primary energy of fuel by the global transport's carbon intensity, you get 3.4 gigatons of CO2, which is a lot. But it's about 11% of the roughly 30 gigatons of CO2 that we need to displace from current or projected, actually, utilization across the entire economy. But if you then look at the negative emissions from 50 exajoules of biofuels, they're almost twice as big. And it's about a third of the total negative emissions needed across the entire economy. So in my opinion, negative emissions are going to emerge as an important and quite possibly the most important driver for biofuels going forward. I want to alert you to this paper. Came out a year ago. It's a big effort, 23 authors. I want to acknowledge Greg Beckham in particular from NREL, who co-led this effort with me. We call it Toward Low-Cost Biological and Hybrid Biological Catalytic Conversion of Cellulosic Biomass to Fuels. There's a lot in that paper, but here are 3 strategic points. 1, small molecules are inherently less expensive to produce than large molecules, especially from lignocellulose. 2, there are alternative processing paradigms with potential to produce low molecular weight fuels or fuel precursors at much lower cost than the thermochemical pretreatment fungal cellulase paradigm. And 3, catalytic conversion of low molecular weight intermediates, notably ethanol, to hydrocarbon fuels is a promising approach to bridge the gap between the fuel molecules that are most readily produced biologically and those that the world would most value from biomass. I'm watching my watch here. We're going to leave time for discussion. Forgive me for the rapid pace. So let's look at this point. Small molecules are inherently less expensive to produce than large molecules. So my friend Costas Marinas at Penn State and his students compiled this. It was sort of a big data survey of all the biologically produced products ever reported in the literature, the maximum reported yield and the maximum reported titer in the broth. The blue is the absence of aeration, anaerobic processes. The magenta is in the presence of aeration. So there are 7, and only 7 at the time of this survey at least, 7 anaerobic products are more reduced than glucose, a requirement for a fuel, and have at least one of the following desired features: reported yield greater than 70% of theoretical, reported titers greater than 40 grams per liter, boiling point less than water. Every one of those products has 4 or fewer carbons. And so for reasons we elaborate in the paper, small molecules are less expensive to produce biologically than large molecules, especially anaerobically, which is a virtual requirement for fuels, and especially from lignocellulose. Well, it turns out ethanol is the only compound that has all of those properties. It's also in a class by itself for easy product recovery. So in the United States, at least, lots of academic and to some extent in the past, at least, industrial interests were saying, oh, ethanol, that's old news. In my opinion, it is the logical point of entry for lignocellulose processing. And as we wrote in the review, ethanol occupies a singular space in the bioproduct landscape. It's the lowest cost liquid fuel or fuel intermediate produced biologically today, and in our view is likely to remain so. Well, this idea of alternative processing paradigms, and I'm going to present the one that I am working on with a network of people around the world, consolidated bioprocessing with co-treatment. Sorry, I haven't come up with a better name yet, but that one's got some historical roots. So speaking of history, let's look at how we got here. Back in 1945, the US Army Natick Lab initiated research because canvas made of natural fibers was not holding up well during the Second World War in the South Pacific. Well, by the mid-60s, synthetic fibers emerged, and the Natick lab, 2 hours south of me here in New Hampshire in the United States, it refocused on cellulosic biomass to food and fuel, and they asked, what microbes are the best cellulase secretors? The answer was aerobic fungi. I think they were correct in that, but they didn't ask, for example, which we will in this talk, what is biology's best systems at deconstructing cellulosic biomass? They didn't ask that. In fact, they observed thousands of microorganisms have the ability to grow on cellulose. And although many of these grow quite rapidly, only a few produce extracellular cellulases capable of converting crystalline cellulose to glucose in vitro. So folks, we are talking, on the order of 40 years ago is when the direction of this field was really determined that most people are still following, which is to use these aerobic fungal cellulases. Well, we can add to that. It was also asked what can be done before biological processing to enhance enzymatic solubilization. That led to thermochemical pretreatment. So this paradigm of thermochemical pretreatment and fungal cellulases was established, again, over 40 years ago in 1980. Lots has happened since then. In 2016, there were half a dozen pioneer plants built around the world, all based on this concept. By the way, 2 in Brazil, and are now being replicated by Raízen. Raízen is the only company in the world that is replicating cellulosic ethanol plants. So if we look at these 2 processing paradigms, for consolidated processing with co-treatment on the right, we avoid the 2 factors that are responsible for the high cost of the conventional paradigm, which is the pretreatment itself and the added enzymes. So the basic idea of consolidated bioprocessing, and again, forgive me for going fast, but I do want to leave time for discussion. And we can talk about personal aspects if that's most interesting to you. You know, there are 4 different biologically mediated events. People started off thinking about those happening in simultaneous hydrolysis and fermentation, SHF, and then combining the two, the biomass deconstruction and the hexose fermentation, SSF. And if you do all 4 of these steps in one consolidated unit operation, this is called, including the production of the enzymes, this is called consolidated bioprocessing, or CBP. All right. And so we could ask this question, which could have been asked a long, long time ago. We had the methods to ask this a long time ago, but it's not the question that was asked. I've reviewed this field a lot, and I know the literature very well. So the question is, what biocatalysts are most effective at lignocellulose deconstruction? If you will, what is nature's best? There are lots of architectures out there, and I have my ideas about why this question wasn't asked for decades, but I'll leave that aside for the moment. This was we started to look at this starting about 10 years ago. This was our very first look at it. It's not definitive by itself, but we noticed that this microorganism Clostridium thermocellum, a naturally occurring anaerobic thermophilic lignocellulose fermenting microorganism, achieved much better carbohydrate solubilization than fungal cellulase and yeast. So, this led to extensive comparative studies in at least 4 papers, multiple feedstocks, multiple substrate loadings, presence or absence of microorganisms, different catalyst loading, different range of particle size, etc. And we also validated and cross-checked results with several labs. Here is a summary figure, which I will take a minute to explain. So the bars reflect the fractional conversion of initially insoluble carbohydrate. All right, and we looked at switchgrass, a herbaceous feedstock. We looked at poplar. We looked at corn stover. We looked at corn fiber, the part of the corn kernel that is left over after you do conventional ethanol production. We also looked at pure crystalline cellulose. The reddish bars here are fungal cellulase. Oh, and by the way, for switchgrass, we looked at multiple different lines of switchgrass that were bred to be less recalcitrant. So one approach to overcoming the biomass recalcitrance problem is to develop less recalcitrant feedstocks. So we looked at multiple ones of them. But here's the message, folks. You can compare, for any binary comparison, you can compare C. thermocellum with no added enzymes to industry standard fungal cellulase. This is all with no pretreatment. And we see that the bacterial anaerobic system is anywhere from 2 to 5-fold more effective than industry standard fungal cellulase. Let me zero in on one of those. So here we have corn stover, not particularly different from bagasse, although not identical, but it's a herbaceous crop residue. And so if we blow that up a little bit, here are 3 different studies. Only one of which was done by my group, and ours is right in the middle. We got 21% of the carbohydrates solubilized with standard, we used Novozymes, the other studies used Genencor. They aren't particularly different. Thermophilic cultures, by contrast, monocultures get 66% solubilization, and co-cultures, in a paper we published last year, get 75% solubilization. So nature offers biocatalysts that are really much, much better than commercial fungal cellulase preparations. Key message. It's also true that nature offers biocatalysts that readily consume all of the biomass sugars at once. These are data for a hemicellulose fermenting thermophilic bacteria. We did fed batch fermentation of glucose, xylose, galactose, arabinose, and mannose. And as you can see, they're 20 grams per liter each, 100 grams per liter total for 5 sugars. They're all consumed simultaneously. After decades of work with yeast, there's still no yeast strain that will do that. So part of my message is, let's go to nature and really, again, start with nature's best capability. Now, I will acknowledge yeast is probably nature's best ethanol producer, But it turns out in terms of the economics that having a really good substrate utilizer is much more important than having a really good ethanol producer. Although you've got to have a good enough ethanol producer, that's still a challenge for this CBP approach. So another question, how best can we give biology a hand? How best can we augment the biological deconstruction? Well, for at least 40 years, the field's answer has been thermochemical pretreatment, but that's not the way that nature does business. My son is a dairy farmer, and what nature does is the cow eats the grass, sends it down to the bioreactor, and then sends it back up and exposes more surface area by chewing. And so the rumination increases the forage particle surface area by up to 10,000-fold, according to this review by my friend Paul Weimer, and it requires 2% of metabolizable energy. So if we're going to rethink our deconstruction microorganism, we're going to go from fungal cellulases to thermophilic bacteria, we can also rethink how we're going to give biology a hand. Yeast is an amazing microorganism, and I honor this all the time. In Brazil, your ethanol industry typically inoculates their process once a year, and they maintain or develop a yeast culture without a completely sterile feed, and that's because they put sulfuric acid in the recycle line, and yeast is a really tough microorganism to chemical inhibition. It's not a particularly tough organism to mechanical disruption. By contrast, if we look at these thermophilic bacteria, there's nothing special about them in terms of chemical inhibition, but they're very, very tough to mechanical disruption. So this concept of co-treatment, which we patented a couple of years ago, is mechanical feedstock disruption during fermentation in lieu of thermochemical disruption prior to biological processing. And the very first demonstration, we said, well, look, let's see if this works. Actually, first, let's see if microbes can survive aggressive milling. So essentially took a piece of 4-inch process pipe, we made that into a fermenter, and we added stainless steel beads and stirred them during the entire fermentation. And as you can see, Clostridium thermocellum on a soluble substrate is slowed down a little bit, but not very much by the milling. By contrast, yeast is just blown out of the water. It cannot metabolize. It's just not as mechanically tough. So I showed you this graph before, but before I was showing it without any pre-treatment or co-treatment. And now I show two new things. The dark blue is the added benefit due to genetic modification of the plants, relatively modest. The light blue is what happens if you mill during fermentation. You get up to over 90% of the carbohydrate, including both C6 and C5 sugars, over 90% of the carbohydrate released from both woody and herbaceous feedstocks. Now, this is indicative of potential. Added work is required to realize this at high solids loading required for industrial application. Again, I apologize for racing on. It turns out, though, it's important to realize that we get profound liquefaction during the biological processing. So there's this is a log to the base 10 scale. As a function of the fractional conversion of carbohydrate, we get about a 2,000-fold decrease in viscosity during fermentation. And so I think I won't elaborate this point in much detail, but the idea is if you want low energy, it really helps to have fermented material, but fungal cellulase doesn't get you very far. C. thermocellum without pre-treatment gets you a lot farther, and so all of a sudden these overlap. So interestingly, rather than non-biological disruption before biological processing, which is pre-treatment, co-treatment entails biological attack before non-biological disruption. So we let biology at the feedstock first. Okay, so what about economics? This is looking at potential. It's not fully realized, but this is a paper with NREL co-authors where we looked at payback time, which is simply the capital cost divided by the annual revenue per year, has units of time. We looked at it for the conventional SSF process as specified by NREL, and for the consolidated bioprocessing with co-treatment. You notice the blue curve. You notice two things. The CBP has 8-fold shorter payback period, and the curve is rather flat. economic feasibility at tenfold smaller scale compared to the conventional paradigm. Again, this requires development to realize assumed performance. I'll talk about commercial deployment soon. And there are various advantages, most of which I've mentioned, and I don't want to catalog again because I don't want to take up too much time. A key dilemma, though, is that we've said that small molecules like ethanol, and probably particularly ethanol, are less expensive to produce biologically than large molecules. Yet very clearly, most of the world is heading towards batteries and electric vehicles to decarbonize light-duty transport. And the fuel molecules the world would most value from lignocellulose are large molecules for aviation and heavy-duty transport. We think, and again, it was the main subject of that review I introduced earlier, we think that so-called hybrid processing is a promising path to resolution. And the idea is that first you ferment lignocellulose to small molecules, doing what biology does well, and then you use industrial catalysis to convert small molecules to hydrocarbon fuels. Lots of companies are looking at this. There have been 50 offtake agreements in the last 2 years. And again, quoting Jim Beilenberg, for sustainable aviation fuels from lignocellulose, biological production of ethanol, followed by upgrading to hydrocarbons, is among the most promising routes, and low-cost scalable cellulosic ethanol is the key missing piece. And again, lots and lots of companies looking at this, a bunch of announcements just in 2020, just last year. And here's a paper we published in PNAS, Techno-Economic and Life Cycle Analysis of Catalytic Conversion of Wet Ethanol into Fungible Blend Stocks. This bar graph here shows that the cost per gigajoule on a low heating value basis is actually getting very close. If you start off with wet ethanol vapor, you either can purify it or you can catalytically convert it to high molecular weight fuels. And the cost, according to this projection, is rather similar, which is really remarkable if that can be realized. We could talk about that particular catalytic upgrading technology and its status, because I'm quite familiar with it. I'm not a driver of that. I just have friends that are very active in that. And so if you look at life cycle greenhouse gas emissions, again, from that paper, the short message is that the catalytic upgrading doesn't add much to the ethanol. So if you have low carbon ethanol, you're going to have low carbon, high molecular weight fuels. So this leads to this idea of CCBP having this potential for radical cost reductions, led to the formation of the Advanced Second Generation Biofuel Laboratory at the University of Campinas. It is co-located at CBMEG and the Faculty of Chemical Engineering. And we're still going to be recruiting more people to work on this, we hope. So if that's of interest to you, get in touch with me. But the basic idea is was established, FAPESP funded under the auspices of the, Luana's picture got there a little early. I didn't animate that correctly. Under the auspices of the Sao Paulo Excellence Chair, we have two focus areas: microbial cellulose utilization, the front end, the extracellular piece, and biotechnology to persuade these nature's best microorganisms at deconstructing cellulosic biomass. We have to make them better ethanol producers. That's the short focus there. And so Evert Helverhoff leads our groups both at Dartmouth and at the A2G lab on microbial cellulose utilization, Dan Olson on the biotechnology. Adriano Mariano is the responsible professor from Unicamp, and Luana Bergamo is the assistant director located at CBMEG. I want to just tell you a little bit about a startup company, and then in about 5 minutes, we will have 20 minutes left for discussion. So I may have totally overwhelmed you with the speed of this, but at least for leaving some time to talk about whatever's most on your mind. So I'm leading a startup called Terragia. And some of these themes we've already talked about. To respond to the climate emergency, we need cellulosic biofuels. They're actually projected by the IEA to be needed to meet the climate mitigation targets. They need a 40% annual compounded annual growth rate. Sustainable aviation fuels need a 65% growth rate. and negative emissions need a 78% growth rate. A 14% growth rate is predicted. So this is a big deal. I've made some of these points already. I think I will skip this in the interest of time, except with negative emissions. Fermentation off gas is the lowest cost carbon capture and storage opportunity, bar none. And for cellulosic ethanol, about 70% of the feedstock carbon is capturable, although most of the energy ends up in fuels, and that's not widely realized. But to fully realize this, with honoring very much Hyesen's pioneering, better biomass conversion technology is needed. This plot I've already shown you for the payback time. And so this is part of Terragia's pitch deck. So we show that again, but you've heard that story. We incorporated in October of 22, 7 months ago. 8 months maybe. We are a spin-off of Mascoma. Our business model is to provide technology to biofuel producers through revenue from licenses and production JVs. We want to work with producers, not compete with them. That includes Brazilian producers. We've got quite a bit of IP. We've got maybe now 5 FTEs, so we're a very small company. And we've got quite a bit of non-dilutive funding and key relationships. We've talked about CBP. It's radically different from the conventional paradigm, and it's distinguished by better biology, fewer process steps, and avoiding co-treatment. So if you look at, for example, applying CBP to corn stover in the near term, this is for a small co-located cellulosic ethanol plant at a host production facility. The cash cost is the ethanol cash cost is about $2.3 per gallon of ethanol, which is about half what you can sell ethanol for now. A capex of $28 million, which may seem like a lot, but in cellulosic biofuels 1.0, all of those plants cost at least $100 million, and the highest one was $500 million. The average was about $250 million. So we're essentially an order of magnitude less expensive. So we're going to try to roll this technology out using very small plants. We're interested in doing that in the United States with corn processors. We're very interested in doing that in Brazil and don't yet have our relationships fully solidified in Brazil, although we're working on it, working on bagasse or perhaps cane straw. If you think about the projected economics based on the model I've already shown in the paper from NREL, the ethanol cash cost, and I apologize that this is $1 per gallon of gasoline equivalent. So you could multiply this by 3.8 to get dollars per liter of gasoline equivalent, and they're all low numbers. The capex per annual gallon, and then the very strong negative emission potential, depending on which streams you capture. You can get minus 170 grams of CO2, i.e. net consumption of carbon dioxide. We are raising investment, a Series A of approximately $5 million of new money plus 2 or 3 of non-dilutive money. So let me just summarize. Oh boy, look at this. We got some formatting issues. Let me very quickly fix at least one of them. I'm not quite sure what happened there. But let me very quickly summarize a few points. We talked about way back when sustainable biofuels. CO2 removal is important. Nature offers biocatalysts that are better at lignocellulose deconstruction than commercial cellulases. I think that opens up some big possibilities. And lignocellulose to ethanol to hydrocarbon fuels is a leading approach for making high molecular weight fuels. We talked about consolidated bioprocessing with CBP. And so it's an alternative paradigm with potential for low cost due to better biology, fewer process steps, and avoiding thermochemical pretreatment and its many limitations. Again, though, I want to stress it's not something that the next step is not to build a plant. There is laboratory research that needs to be done to further improve the technology. And as far as making second generation biofuels happen, Brazil is not a global leader, but the global leader. And the A2G Lab and Terragia are both working to advance CCBP, working in partnership with others. So folks, we've got most of 20 minutes left. Thank you for your attention. Apology for the speed. I'm going to stop sharing my screen. And you can take this discussion wherever you want. You can ask me questions about what I've said. We can talk about, my perspectives on the field. We can talk about my personal background, as Gonzalo has suggested. Really, the rest of our time is up to you. So what's most interesting to talk about, folks?
Lee, thank you very much. It was brilliant, great. And the time, I like very much this because I was all the time paying intensively attention to the logics of what you said. I would like to ask if someone want to make questions. I have some, but please, we have here Marilene Pavan. She is a PhD and she is working in Lanzatech.
Hi, nice meeting you.
Nice to meet you. Lanzatech in the US or in Brazil?
In US.
Oh, so in
I'm
Illinois,
in Chicago.
Then?
Yeah,
Chicago,
correct.
Yes. So you probably know Steve Brown and what is it, Sean Simpson?
Yeah, absolutely. Anyway. Yeah.
Yeah, very
I know
good.
them both. Yeah.
Give them my regards, please.
Absolutely, will do.
So, Lee, we agree. I have some question about I didn't understand exactly. I agree totally in the CBP concept. I think that we have a lot of stage. Each stage that you have is a lot of problem, a lot of money to be expended, and inefficiency that you add to the system. For sure, it's wonderful if we have the possibility to do everything, let's say, in one step.
Yep.
We in Grand Bio, we work at exactly with the same concept. We look at the lots, how the nature and how the calls in particular made the process. For example, the tone of the call, the way that it handle the biomass instead of meshing. I don't remember the name, but I do believe that this is the way to go, to understand how the animals make the process and do a similar thing. I didn't understand exactly when you say that you can put your bacteria, right? It's a bacteria.
Yeah, it is.
And you put together this with the biomass. Let's think that we are in the lab.
Yep.
How to go from the biomass to the ethanol? What would be the steps?
Yeah, so basically, I mean, in the lab, where you're looking for proof of concept rather than industrial demonstration, you would mix up some growth media. You would put in some lignocellulose, probably 4 millimeter particle size or less. We often work with less because it's easier to handle at small scale, but I think it's not, the conversion process doesn't fall off much. As long as it's down to about 5 millimeters, that tends to be good enough. And so when we're doing experiments in the lab, we put that in an autoclave, whether it's a fermenter or a serum vial or something. We bring it out, we let it cool, we inoculate it with microorganisms. We don't add any enzymes, we don't pre-treat. Sometimes we mill during fermentation, or we do what we call ferment, mill, ferment experiments, which is a more efficient way to screen milling technologies.
Sorry. May I interrupt to ask you additional questions? That means you have your bacteria in a media, a culture media with particles of biomass in 5 millimeters, let's say. And then you have the possibility to mesh, let's say, this material utilizing the beads that you showed. You have shown, right?
It's true, but it's also true that, I mean, when we look at in my opinion, one of the things this field has really gotten wrong in the last 15 years, I think people have tried to do things in the wrong order, and they've often tried to do too many new things at once. And so the initial application on corn stover, for example, I don't think we'll even mill substrate at all. I don't think we'll just use better biology. So the key is that we're able to, the microorganisms that make the ethanol also make the enzymes. They also make better enzymes than fungal cellulases. And we have co-cultures that readily utilize not only the C6 sugars, but the C5 sugars. So the the basic process is pretty simple. It's like you feed particles to microorganisms and they ferment them to ethanol without adding much. And we anticipate commercializing it first without doing any milling. But I think to get to BTU competitive or gigajoule competitive costs with gasoline, I think it probably will be necessary to mill, but we don't want to try to do too many new things at once. So we'd like to prove the biology commercially before we add the milling.
Okay, then continuing the process, you have the bacteria in your media with
Yep.
small pieces of biomass.
Yep.
This small piece can be produced by regular machines that are
Yeah.
very
Yeah, I
simple.
don't think nothing special about the small pieces.
Okay. How long it will take the process to have the sufficient hydrolysis and
Yeah.
ethanol production?
Yeah, so that depends. When we're doing kind of screening studies in the lab, typically focusing on how much substrate we can solubilize under routine conditions, about 5 days, but we have an approach that it's a very well articulated hypothesis that I believe will probably be proven, but hasn't yet, to cut that in twofold or more. So I'd like to think that we're heading towards about a 2-day total reaction time for fermentation and hydrolysis, but we're not there yet. I try to be careful distinguishing between aspirations and achievements. So we do it in the lab routinely in 5 days. Usually, by the way, I think this field has suffered a lot from high expectations and perhaps overselling. So I try to be cautious. Most of the lab work we do is at solids concentrations that are less than commercial. To make this process work, and it's one of the research challenges, we need to function at yet higher solids concentrations and have undiminished performance. So that is something we haven't fully realized, but we do think there's a very strong rationale based on just starting with nature's best, as I said. But am I answering your questions, Gonzalo?
Yes. I'm trying to understand. When we think about this in a commercial plant, a small
Yep.
one, I think the great thing that you have with this idea is that you have the opportunity to produce small second generation plants, right?
Yep.
And this is very important.
Yep.
The process, both hydrolysis and fermentation, needs to be sterile, right?
At this time, yes. We aspire to, we are just today, I was working on a proposal to, as you know, the yeast fermentation that you do so well in Brazil is not sterile. I think there are reasons we may be able to get there, but we're not there yet. We aspire to getting to the point that we can maybe pasteurize rather like you do with cane juice, but not sterilize. But we have not proven that yet. So I mean to be making a presentation about potential. I think the potential is real and almost obvious, by the way. If you use better biology and you don't pre-treat, you may be able to do some things much better, but we don't have everything figured out. And by the way, as I go around a second time in a startup company, the CEO I work with, Bill Brady, and we don't talk more than 5 minutes than talking about mistakes that were made by us and others that we don't want to repeat. One of those, frankly, is piloting too soon. Everybody wants to give you money to build a pilot plant. The government does, the VCs do, because that's the path to revenue and deployment, and we all want revenue and deployment. But the problem is, and this movie's gotten shown many times, people build a pilot plant or even a commercial plant knowing they haven't really fully worked out all of the technological details. But it's kind of like, oh, well, the story will catch up. But you know that's not what happens. They make big promises to people, and gradually the stories they need to tell to keep raising money and the reality get further and further apart, and eventually it collapses. So we do not want to repeat that. And so even though I suspect we could go and tell a big story and get money for piloting, we know the real advances are still things that can be done in the lab. The other thing is that lab work is cheap compared to piloting. Piloting's expensive. So we fully want to get to pilot plants, but only when it's the right next step. So we're trying to think about how do we move this forward and always move forward and never like tell a big story and then have to sort of back up to, fill in behind our stories. So, we're pretty serious. We're very serious about the science, but we're also very serious about deploying this in the world. And right now we're talking to investors. Next time I come to Brazil, I hope to talk to more producers and investors because we think the time to make this happen has arrived. But from the
I
group,
agree with you. For that reason, I'd say the following: 2G is an enormous potential that will be fulfilled in the future. However, this is a big challenge, big scientific and technological challenge. To pioneer this, you need to have a lot of courage. And for sure, we are going to make a lot of mistakes. Yeah, this is natural. But this is the way how the world learns.
Yep.
Our experience in Grand Bio, not only ours, but from everybody. Everybody thought that pretreatment was something that would be under control because we had the big shots in the cellulose industry that were used for 100 years to move biomass, to mash biomass, to do everything that you need in the big industry with biomass. And that enzymes and the second generation yeast would be rocket science, very difficult to, as you said, biology run nicely. We have good enzymes, we have good yeast, we have everything, but pretreatment is a big challenge. And when I was in Grand Bio, we are filling a patent exactly about what you said, to make biological and mechanical treatment happen at the same time and find the correct organism to support this strain, exactly as you are doing, and I totally agree with this. The question really is how far can we go without the need of this mechanical help, let's say. What do you think?
Well, I think we need to choose the easiest feedstocks first. And this was a mistake Mascoma made. Mascoma went to try to do hardwood chips in northern Michigan, Well, that is just a much harder feedstock than agricultural residues. And so I think if we choose the right feedstocks first, we're not going to need milling right away, which just gives us a little more time to get that piece really working. And meanwhile, just use better biology. I mean, it's kind of obvious. The better and this is really true, the better biology you use, the less help biology needs, whether it's from pre-treatment or co-treatment. And so I think that's the direction that that's really going to pay off here. But I want to take time for questions. By the way, if people have questions they don't get a chance to ask and want to email me, you're perfectly welcome to. But members of the group, questions, comments? Yes, please go ahead.
Hi, Professor. My name is Lucas Pereiras. First off, I just would like to say it's a pleasure to meet you, even if it's online, having followed your work for many years. So I have a startup that develops technology for enzyme production.
Oh, good.
And we work with fungi. And it's not our main focus, but obviously we look at the 2G ethanol market. Yeah. And your technology is very exciting. So my question here is, on your opinion, do you see room for fungal cellulases in this market in the long run, or no, you think they'll be left aside?
Well, I feel confident as a scientific and a technological statement that nature has deconstruction systems that are better higher functioning than aerobic fungal cellulase, not only now, but I would even venture to say than aerobic fungal cellulase will ever be. That's a presumptuous statement, but on the other hand, I have followed the literature for a long time, including the patent literature, on actually improving cellulases. And it's considering that these have evolved over literally billions of years and many, the trial and error of nature's laboratory, they've evolved into different niches, et cetera. So my opinion is that they're just not the best. However, i.e. fungal cellulases, in my opinion, there are better systems in biology. The question, though, and it is still an open question. I mean, I have my hunch, but I might be wrong. And people who know as much as I do probably have a different answer. I'm sure that's true, actually. I think what it really depends on is, can we get the microorganisms that are nature's best at lignocellulose deconstruction to be good enough at making ethanol, or for that matter, other products? And if that answer is true, then I think the fungal cellulases in time will end up fading away from a technological point of view for this particular application. On the other hand, that has not been shown yet. And so it is possible that the anaerobic thermophiles that appear to be nature's best at taking apart lignocellulose, it's possible, it just won't be possible to, it's conceivable that we will not be successful, we and others, no one will be successful at getting those bugs to make ethanol well enough, in which case systems with fungal cellulase may persist. So I can't tell you that they won't persist. What I can tell you is, if we can solve the challenges to consolidated bioprocessing with co-treatment, I think it has potential to be a much cheaper, a much less expensive, and much simpler and much more operationally robust process. But potential is just that. It has yet to be proven. I'm trying to give you a fair answer. So I don't really know the answer, but it depends on the variables I've described.
No, that's great. Well, thank you very much.
And by the way, most business decisions are based on things you can do in the relatively near term. In the relatively near term, there's going to be a lot of people buying fungal cellulases. So I wouldn't worry too much that in many years down the road, there may be a better answer. Other questions from the group? Yes,
Thanks.
Gonzalo.
Let's first see if someone else has a question, because I have one.
Okay, I'll take whoever wants to
Yeah,
speak.
guys, any question? So let's go then. Lee, one of the things that we have tried, we began actually in the past, was to try a mixed culture. Actually,
Yes.
we are just now trying with two kinds of different yeast species.
Yes.
What do you think about this possibility, to have mixed cultures from bacteria and yeast, for example?
I think mixed cultures can be a very good idea, and I'm going to give you a somewhat biological reason. I think there are many desirable industrial phenotypes out there that have proved very difficult to move from one organism to another. I mean, and a good example is yeast, Saccharomyces utilizing pentose sugars. If you write out the biochemistry, it shouldn't be that hard. And people have tried and tried and tried, and there is still no yeast in this world that will use xylose equally with glucose at the same time as efficiently and all the rest of it. And so what I think this tells you, and if I look at the thermophilic bacteria, for reasons I don't understand, but it's very clear, evolution gives us cellulose specialists like Clostridium thermocellum that don't ferment this. They solubilize hemicellulose, but they don't ferment C5 sugars. And they give us other hemicellulose fermenting microorganisms that don't ferment cellulose, but ferment hemicellulose sugars. Now, some people look at that and go, oh, fine, well, we'll engineer C. thermocellum to use 5-carbon sugars. I think it's a much better idea to use co-cultures. And furthermore, people are concerned about stability with co-cultures. Well, if each of the microorganisms has a distinctive niche, for example, an ability to use a substrate the other one can't, this will be a very stable co-culture. So I'm actually a big fan of co-cultures.
Lee, wonderful. Really, I really appreciate it a lot. I copied several of of your slides. If you could send me your presentation,
Sure,
because
no
it will be public now at the YouTube. But I think you finalize with a very important concept. We humans are actually co-cultures. We have much more bacteria in our body than cells that we can call ourselves. Actually, everything is ours. I do believe that the challenge is big. I really love your approach of being a very good scientist, and from the science, go to the technology and then go to the business. I think this is the way to go. It's a big pleasure, my friend, to have you here. Your talk was great for everybody, but especially great for me. Next time that you come to Brazil, please let me know so that we can continue our talk.
Sounds great. I would look forward to that.
Way.
I would look forward to that, and the features you described about science and then trying to make it happen in the world. I see the same things in you. So it's good to be in touch. And again, if people have any follow-up questions, I'll send you the slides. If people have any follow-up questions, just let me know.
Yes, I will share your slides with the people, with everybody in the course, including the professors.
Very good.
Thank you, my friend. See
Take
you
care.
very
Ciao.
soon.
Yeah, see you.
Tchau,
Bye.
pessoal. Tchau, todo mundo. Até a semana que... Aliás, semana que vem nós não teremos, porque é no feriado, logo em seguida. Um abração, pessoal. Até logo. Tchau, tchau.
Abraços.